Hello, and welcome to this online lecture. My name is Patty Kokish, and I teach in-person and online math classes in the Northwest region. Today, I'm going to be going through topics from Chapter 9 for Math 200. This is week 10 of your class. You had your midterm last week. So Chapter 9 is all about estimating the value of a parameter. So we're going to start with Section 9.1, which is estimating a population proportion. So the objectives in this section are first to be able to obtain a point estimate for the population proportion, which is a pretty easy task. And the second objective is to construct and interpret a confidence interval for the population proportion. And then thirdly, we will also learn how to determine sample size that would be necessary for estimating a population proportion within a specified margin of error. So let's start with the first objective, which is obtaining a point estimate for a population proportion. So a point estimate is the value of a statistic that estimates the value of a parameter. So basically what we do is we just take p hat, that's going to be our point estimate, and it's going to be x over n. Now, for example, the point estimate for the population proportion, it's going to be called p hat. X is going to be the number of individuals in the sample, and n is going to be the sample size. X is the number of individuals in the sample with a specified characteristic. So for example, if you're looking for people with brown eyes, you would count the number of people who have brown eyes and then the total number of people that you sampled. And that would give you your population proportion when you divide. So let's look at an example here. So in July of 2008, a university poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. So if we'd like to obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty, then what we would want to do is we'd want to calculate the number that were in favor, which in our case was just 1,123, and then we want to divide by the total number who were surveyed, which is 1,783. So you'll see that's what's done here. P hat is 1123 over 1783, and if we divide this, you get something like 0.63. So that corresponds with about 63%. So that means that about 63% of registered voters nationwide are in favor of the death penalty. But this is just from a sample. So the next thing we're going to do is actually expand on this and learn how to extrapolate it so that we're talking about the entire population. So that's what objective 2 is all about. So we want to construct and interpret a confidence interval for the population proportion. So the first step is always to take your sample, get your p hat, and then what we do is we use it to create an interval in which we think our true population proportion might lie. So a confidence interval for an unknown parameter consists of an interval of numbers based on a point estimate. So that's what I was just talking about. The point estimate, that's from your sample, and then what we do is we add and subtract this margin of error in order to end up with a confidence interval for our unknown population parameter. The level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. And we denote the level of confidence as 1 minus alpha times 100%. So we're going to have a lot of practice with this today, figuring out what alpha is, but this is kind of how we denote our level of confidence. So for example, if we have a 95% level of confidence, if you think about that, 100 minus 95 gives you 5%, and then what we want to do is we want to change that back into a decimal. So if you think about changing 5% into a decimal, you're going to get 0.05. So that is your level for alpha. And what this implies is that if 100 different confidence intervals were constructed, each based on a different sample from the same population, so we took 100 separate samples, we would expect 95 of those 100 intervals to actually contain the parameter, and 5 would not include the parameter. So the whole idea is that this isn't perfect. When we take a sample, we do the best job that we can, but nothing's ever going to be perfect. So what we end up with is an interval. And hopefully our interval contains our true population parameter. But if we have a 95% level of confidence, we would expect 95 of our 100 intervals to contain the parameter and 5 not to. If we were constructing a 90% confidence interval, that would mean that 90 of the intervals would contain the parameter and 10 wouldn't. Or we could go higher, like 99% level of confidence. That would mean that we would expect 99 of our intervals to contain the parameter and 1 would not. So in order to actually find our confidence interval, what we do is we take our point estimate and then we add and subtract something called the margin of error. The margin of error of a confidence interval just estimates a parameter. It's just basically a measure of how accurate our point estimate is. Okay, so we're going to look at how to calculate that, but you'll notice it's very similar to stuff that we have already done in this class. Margin of error depends on 3 different things. The first thing is the level of confidence. So as the level of confidence increases, the margin of error is going to increase. So if we want to be 99% certain, then our margin of error is going to increase. But if we're okay with 90% confidence, then we'll have a smaller margin of error. Sample size also plays a big role in this. So as the size of a sample increases, margin of error actually decreases. So as we can take a larger sample, if you think about it, that's going to be more expensive, more time consuming, but it does create a smaller margin of error, which is desirable. And then standard deviation of the population also plays a role. So the more spread out the population is, the wider our interval is going to be for the given level of confidence. So if everyone's really grouped together, you have a very small standard deviation, then you'll probably have a fairly small margin of error. But if you have a very large spread in your population, then you could have a very large margin of error due to the standard deviation. Okay, so let's talk about the sampling distribution of p hat. This is something we've already talked about, but for a simple random sample of size n, the sampling distribution of p hat is approximately normally distributed with a mean of p and a standard deviation found by calculating p times 1 minus p, then dividing by n and taking the square root of that whole thing. And then it was also required that n times p times 1 minus p be at least 10. The other thing that has to be true is that trials need to be independent. So if you're sampling from a finite population, so something that's countable, your sample has to be less than or equal to 5% of the entire population. This is not typically an issue. Normally, we don't end up with too large of a sample size, but if you were trying to find out information maybe about a certain class or something like that, or a very small population, this is something you might run into issues with. Okay, so if we'd like to actually construct our confidence interval, and it could be 90%, 99%, 98%, could be anything. Let's suppose that a simple random sample of size n is taken from a population. A 1 minus alpha 100% confidence interval for p is given by the following quantities. So we have a lower bound and an upper bound. For the lower bound, we take our point estimate, our p hat, and we subtract z alpha over 2, which is called our critical value. I'll show you guys how to find that. And then you multiply that by p hat times 1 minus p hat over n, and it's the square root of that entire quantity. And then for the upper bound, you do the exact same thing, but instead of subtracting, you actually add. And there's a note at the bottom here. It also must be true that n times p hat times 1 minus p hat has to at least be 10, which we already talked about. And we have to have independence. So our sample has to be less than or equal to 5% of our entire population. We also need to know how to interpret a confidence interval. This is a really important part of statistics, is being able to actually take our results and interpret them. So in order to interpret it, basically what you can say is that a 1 minus alpha 100% confidence interval indicates that 1 minus alpha times 100% of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter. So let me reread this with actual numbers in there. So a 98% confidence interval indicates that 98 of all simple random samples of a certain size from the population whose parameter is unknown will result in an interval that contains the parameter. So that means 98 times out of 100, our interval will actually contain the parameter, and the other 2 times our interval will not contain the parameter. Now, margin of error is given by this. This is just what's added and subtracted from our value. It's just z alpha over 2, which we already talked about. That's your critical value. And then that's multiplied by the square root of p hat times 1 minus p hat over n. It's the square root of that whole quantity. Okay, so let's talk back about this university poll. If you remember this, 1,123 people were in favor of the death penalty out of 1,783. And what we would like to do is we'd like to obtain a 90% confidence interval for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So what we're doing is they took this sample, which was probably not too expensive to actually do. They probably did a good job of picking people, and they ended up with this statistic. They had 1,123 people in favor out of the 1,783. Now, what we'd like to do is we'd like to extrapolate that and be able to say what would be our range for registered voters within the whole US. So we'd like to take this and kind of bring it out so that it represents our entire population instead. So what we need to do is we need to define some of these things. So p hat, that's our 0.63, that was taken just by taking our 1123 divided by our 1783. And then we need to make sure that n times p hat times 1 minus p hat is at least 10. And this one, it exceeds it by a lot. If you take 1,783, that's our sample size, multiply it by our p hat, which is 0.63, and multiply that by 1 minus 0.63, we get 415, which is obviously much greater than 10. So that condition is satisfied. And then the sample size has to be less than 5% of the population. We're talking about all registered voters in the US, so our sample size of 1,783 is definitely less than 5% of our population size, so that's not an issue either. So the thing you need to keep in mind is, what is my alpha value? Okay, so if we're talking about, they asked us to find a 90% confidence interval, that means that our alpha is 0.1, which corresponds with 10%. So if you think about it, 90%, that's our confidence interval. So if we take 100 minus 90, you end up with 10%. So your alpha is 0.1. Now, if you notice in that formula that we have to take z alpha over 2. So what we actually have to do is we need to divide our alpha, this 0.1, we need to divide it by 2. So really what we're looking for is z.05. So what you're going to do is you would look in the actual body of your z table, and you'd try to find this value of 0.05. And if you look at it, it's between, if you're looking at positive values, you're going to be looking for 0.95. If you're looking for negative values, you're going to be looking at 0.05. Either way is fine because the distribution is symmetric, but you just have to make sure you understand what's going on, because this is always going to be a positive value here, which doesn't really matter because you just add and subtract it. But if you look it up, you end up with z-scores between like 1.64 and 1.65. The exact value is 1.645. Okay, so that's going to be your value for this. There's also a table in the book that has the most common values. 90%, this is probably something that it would be worth your time memorizing, so you don't have to look it up each time. 90% is going to go with 1.645. And there are a couple other values that are given as well that are very typical. 95% goes with 1.96, and I think 99.7 is maybe 2.236. I'm not entirely sure of that off the top of my head, but it might be worth your time to take a look at those and memorize those, or at least write them down on a little piece of paper so you have them while you're doing your homework. So essentially what we want to do to create our confidence interval is we want to take our point estimate, which is our 0.63, and we want to subtract our critical value, which in this case is 1.645, multiplied by the square root of of p hat, which is 0.63, times 1 minus p hat, which is 1 minus 0.63, divided by n. So if we do this, you have to do it really carefully. You have to make sure that you evaluate whatever is under the square root first, and then multiply by 1.645, and then you subtract that answer from 0.63. And you should get something around 0.61 when you go ahead and do that. And then the second one should be even easier to do because you already have all these values. All you do is, instead of subtracting your margin of error, which is this entire thing here, this critical value multiplied by the square root, instead of subtracting it, you just add it, okay? And you end up with 0.65. One thing I would like to point out is that your p hat should always be smack dab in the middle of your two endpoints. So if you think about what's exactly in the middle between 0.61 and 0.65, it's 0.63, which was your p hat. So that should always be the case. If you get something where it doesn't work out like that, it probably means you did something incorrectly. Okay, so we always want to interpret these after we've created them, but what we can say is that we are 90% confident that the proportion of registered voters who are in favor of the death penalty for those convicted of murder is somewhere between 0.61 and 0.65, or you could say 61% and 65%. Okay, the third objective in this section is to determine sample size for estimating a population proportion within a specified margin of error. So this is kind of a backwards one. Instead of giving us the sample and all of the information we need, what they do is they give us a specified margin of error, and we need to figure out how large of a sample we would need to take. So sample size needed for a specified margin of error, which is called E, and a level of confidence 1 minus alpha, is given by this formula here. So N, that's going to be your sample size, is equal to P hat times 1 minus P hat multiplied by Z alpha 2 over E, which is your margin of error. So it's your critical value divided by your margin of error squared. Just this little fraction is squared. But the problem with this is that the formula uses P hat, which depends on N, which is what we're trying to find. So there are a couple of options available to you. The first thing you can do is you can use an estimate of P hat based on some kind of pilot or earlier study that was done. So if you're studying something that someone has already studied and there's a fairly good estimate already out there, you're welcome to go ahead and use that. However, if that's not the case, what you do is you let P hat equal 0.5, which basically just maximizes your equation. So it ends up being a very, very conservative estimate, which works just fine. So here's our sample size calculation. This is the one we just talked through. And the other thing that this slide notes is that it needs to be rounded up to the next integer. So you always have to round up for these. If you don't round up, then you don't end up with quite a large enough sample size. So you always have to round up when you're solving for sample size. And this is the equation that we use if we're using a prior estimate. So if we have a P hat that we're already going to use. Now, if you don't have a P hat that we're already going to use, so if you don't have a prior estimate, let's say you were the first doing research in this field, so there is no pilot study, or you don't feel comfortable using the results from the pilot study, then you can use this conservative formula, which basically maximizes your N. And what it has you do is it has you take 0.25, which is actually just from taking that maximum value of 0.5 and multiplying it by 1 minus 0.5. So it's still the same formula, but it's just for P hat equals 0.5. So if you did 0.5 times 1 minus 0.5, you'd get 0.25. So that's where this number comes from. So N is just equal to 0.25 times Z alpha over 2, so our critical value, divided by our margin of error, and then that quantity is squared. And again, you round up. So let's say a sociologist wanted to determine the percentage of residents of America that only speak English at home. So we want to know what sample size should be obtained if she wishes her estimate to be within 3 percentage points with 90% confidence, assuming she uses the 2000 estimate obtained from the Census 2000 supplementary survey, which was 82.4%. So she has a prior estimate that she's pretty comfortable with, but she wants to know what should my sample size be if I want to calculate this again. So she's going to use her prior estimate. So since we're using the prior estimate, we're going to use the formula that has P hat times 1 minus P hat. So the first thing you want to do is go ahead and set up all of these numbers, okay? So the margin of error that she wanted it within 3 percentage points. So your margin of error is 0.03. And then Z alpha over 2, in our case, it was a 90% confidence interval. So if you remember, 90% confidence goes with alpha equals 0.1, because that goes with 10%, but we always have to divide that by 2. So really you have Z 0.05, which is 1.645. Your P hat, that was the prior estimate that we're using, that's 0.824, so that was from that census survey. So all we have to do is just plug stuff in and then round up. So we get N equals 0.824, that's our P hat, times 1 minus P hat, so 1 minus 0.824. And then it's multiplied by 1.645, which is our critical value, divided by our margin of error, which is 0.03, but that quantity is squared. So if you do that in your calculator, you can plug it in very carefully all at once, or if you want to plug it in piece by piece, you're going to square this part first. So you divide and then square, and then multiply by these two numbers. and you should get 436.04. So even though you would typically you would follow your rounding rules and you'd get 436. That's not the case when you're calculating sample size. You always have to round the value up so that you have a large enough sample. The whole idea is that if we took only a sample of 436 people, we would not quite meet the requirements that were asked. So what we have to do is we have to round it up by one person, since you can't have 0.04 of a person or 4% of a person. We have to round it up to the nearest whole person. So this 436.04 is actually going to round to 437. So that means that if the sociologist would like to determine the proportion of speakers or Americans who just speak English at home, she has to survey at least 437 randomly selected Americans. Okay, so that was section 9.1. That was all about estimating a population proportion. Now we're going to get into estimating a population mean. So this is pretty much the same idea, except instead of a mean, we actually just have a proportion. Or sorry, instead of having a proportion, we have a mean. So the objectives in this section are obtaining a point estimate, stating the properties for something called a student's t-distribution, which we'll talk about, and then determining t-values and constructing confidence intervals, and then lastly, finding sample sizes. So it's a lot of the same things, but we have this kind of added level of learning about the t-distribution. So let's try this first objective, obtaining a point estimate for the population mean. So a point estimate is the value of a statistic that estimates the value of a parameter. So it's the same thing that it was before, but in this case, the sample mean is going to be our point estimate. So it's going to be X bar, that's going to be our sample mean. That is a point estimate for the population mean, mu. So we don't have the ability to sample everyone in the US. So what we do is we take a sample and we get an X bar, and then we use that to make conclusions about the whole population. Very carefully, of course. So let's do this example here. This is one we've looked at actually before in previous weeks. So we have pennies minted after 1982. They're made from 97.5% zinc and 2.5% copper. The following data represents the weight in grams of 17 randomly selected pennies minted after 1982. And then here are the weights. So what we'd like to do is treat the data as a simple random sample and estimate the population mean weight of pennies minted after 1982. So calculating sample mean should be really easy. This is just finding the average, okay? So all you do is just add up all of those weights that you have, the 2.46, 2.47, and then you'll see the ellipses there. Those are all the ones in the middle. And then you divide by 17, which is the number of observations that they had. And if you do that, you get a sample mean of 2.464. So that's our point estimate of mu. So that's our X bar, which is hopefully giving us a good estimate of our actual population mean mu. So right now it's at 2.464. We're going to do some things with it in a minute where we calculate confidence intervals and all that stuff. But first we need to look at something called the t-distribution. So let's suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t equals X bar minus mu, so it's our sample, our parameter estimate, minus our true mean, and then we divide by S, which is our sample standard deviation, over square root of n, which is our sample size. That is going to follow a student's t-distribution with n minus 1 degrees of freedom, where X bar is the sample mean and S is the sample standard deviation. So let's say we're obtaining 1,000 simple random samples of size n equals 5 from a normal population with mean of 50 and standard deviation of 10. We'd like to determine the sample mean and the sample standard deviation for z and for t. Okay, so you'll notice the formulas are very similar. The only real difference is that for our t, we have S, which is our sample standard deviation, instead of sigma, which is our population standard deviation. This is the whole reason why t is very useful. We don't normally have the ability to know what our population standard deviation is. So what we can do is we can use our sample standard deviation along with our t-distribution in order to still come up with some meaningful conclusions. So here we're first going to start by drawing a histogram for z and t to see what they look like. And this is done, I think, in Minitab. So here's our histogram for z. Looks pretty nice. Our histogram for t. It doesn't look too bad either. But the main conclusion that we want to make is that the histogram for Z is symmetric, bell-shaped, center is at 0, and virtually all of the rectangles are between -3 and 3, just like we would expect. So Z follows a normal distribution. However, T, it's symmetric and it's pretty bell-shaped. It has a center at 0, but if you look back at it, I'll just scroll back there for just a minute, you can see there are kind of these extra tails here that we didn't see before. So the T distribution has longer tails, so it's more dispersed. So it's unlikely that T follows a standard normal distribution. The additional spread in the distribution, though, can be attributed to the fact that we're using S to find T instead of sigma. So we're using the sample standard deviation instead of our population standard deviation simply because we don't know our population standard deviation. And because the sample standard deviation is itself a random variable, so it's not a constant, we have more dispersion in the distribution of T because of the fact that our sample standard deviation is a random variable itself. So here are some properties of the T distribution. The first property is that the T distribution is different for different degrees of freedom. So we're going to talk a little bit more about degrees of freedom in a minute, but it is different depending on the number of degrees of freedom that you have. The T distribution is going to be centered at 0 and it's symmetric. Okay, so that's just like your normal distribution. And similar to the normal distribution, the area is still going to be 1 under the curve. And then the area to the right of 0 is going to be half. The area to the left of the 0 is going to be half. So it's symmetric. And then as T increases or decreases without bound, the graph is going to approach but never equal 0. In addition, the areas in the tails of the T distribution, we already talked about this, is a little greater than the areas of the tails of the standard normal distribution since we're using S as an estimate of sigma. So we're introducing further variability. And then as the sample size increases, the density curve gets closer to the standard normal density curve. So as we end up with really large sample sizes, it does look more and more normal. So this is due to the fact of, the law of large numbers. So basically, S is just going to get closer and closer to sigma as our sample size increases. So because of the law of large numbers, our T distribution is going to look more and more normal. So here's a picture with some different distributions overlaid over one another so you can see exactly what's going on. The blue line is your normal distribution. That's what you're used to seeing. The red line is, maybe it's pink. I'm having a hard time telling. The pinkish line is our T distribution with n equals 15. So you'll see the peak is slightly less high and it has a slightly higher tail. And then the orange distribution is T as well, but this time n equals 5. So these tails are even larger. So you'll see the pink one looks slightly more normal than the orange one because it has a larger sample size. So if we looked at even larger sample sizes, it would get closer and closer to this blue line. But if we had an even smaller sample size, then it would look even more exaggerated from the orange. Okay, objective 3 is to determine T values. So the notation T sub alpha is the T value such that the area under the standard normal curve to the right is alpha. And this figure kind of illustrates this notation. So we have our T alpha here, that's going to be our critical value, and then the area to the right is going to be our alpha. So you have T tables in the back of your book. If you have a graphing calculator, you can also use that to help you find your T values. And there are also a lot of online calculators. So you just have to figure out what works best for you. I typically just use the tables. So let's say that we want to find the T value such that the area under the T distribution to the right of the T value is 0.2, and we're going to assume 10 degrees of freedom. So we're looking for T.2, so T sub 0.2, that's going to be our alpha with 10 degrees of freedom. So what we're looking for is something here, this value right here, where the area to the right is going to be 0.2. So what you need to do is you need to look on your actual table. You're going to go across to where you have your 10 degrees of freedom. And what you'll find is that the T value, your critical value, is going to be 0.8791. Those are all the way at the back of the book. I think they're just right after your Z tables. Objective 4 is to construct and interpret a confidence interval for your population mean. So a few things have to be true, just like normal. So the sample data has to come from a simple random sample or a randomized experiment. Sample size has to be relatively small compared to your population. So again, it has to be less than 5% of your entire population. The data that it comes from, it has to be normally distributed, or the sample size has to be large. And we talked about this before when we talked about our mean. And then this is our formula right here. So it looks actually a lot like our formula for our population proportion. But basically what we do is we take X bar, that's our sample mean, and we add and subtract. So the upper bound is where you add, the lower bound is where you subtract. You take T alpha over 2, that's going to be your critical value. It's going to have n minus 1 degrees of freedom. Okay, so degrees of freedom is always your sample size minus 1. And you take that critical value and you multiply it by S, which is your sample standard deviation, divided by square root of n. So the hardest part about these is learning how to look it up on the table, but it's really not too difficult once you have that. So again, here's this given kind of in a more nicely laid out format, but a 1 minus alpha times 100% confidence interval for mu is given by the following: X bar, sample standard deviation, or sorry, sample mean, plus and minus our critical value times our sample standard deviation divided by square root of n. So we're going to use Minitab to simulate obtaining 30 simple random samples of size n equals 8 from a population that's normally distributed. The mean is 50 and the standard deviation is 10. And what we'd like to do is construct a 95% confidence interval for each sample, and we want to know how many samples are going to result in intervals that contain 50. So if we look at the actual intervals that we have, you'll see here, these are all of our intervals. Let's see, how many intervals? 30 of them. So if you look, it looks like 2 of the intervals do not contain 50, but all of the other intervals, like this one, that has 50 between these two numbers, this one has a 50 between them. They all do, except for this one that's highlighted, sample C8 and sample C28. So it's important to note that 23 out of our 30, or 93% of the confidence intervals, actually did contain our population mean, which was 50. So we can say that in general, for a 95% confidence interval, any sample mean that lies within 1.96 standard errors of the population mean is going to result in a confidence interval that contains the mean. We got a value of 93%, which is pretty close to our 95. And basically, whether a confidence interval contains our actual mean, our actual population mean, depends solely on the sample mean. So if you get a really weird sample, yeah, you're going to end up with a confidence interval that does not actually contain your mean. So let's say we want to construct a 99% confidence interval about the population mean weights in grams of pennies minted after 1982. So this is that same penny problem that we had earlier. So we still have our 17 observations. We do a normal probability plot. This was created in Minitab for us. And you'll see there aren't anything out of our bounds, so that looks good. And then the box plot does not show any outliers. We don't have any asterisks there, so that's good as well. So if we want to actually create our value, what we do is we take our X bar, which this is what we calculated several slides ago. That was our 2.464. That was our average from our sample. And then we subtract our critical value, which is found by figuring out what our alpha is. So in our case, we have 99% confidence. So that means we have 0.01 as our alpha. And if we divide that by 2, you get 0.005. So on your t-table, what you're going to do is you're going to go down to 16 degrees of freedom, because we have a sample size of 17, and we have degrees of freedom of 16. It's always one less. So you go down to your sample size of 16, and you go over until you have 0.005, and you should see a critical value there of 2.921. And then we take that critical value and we multiply it by S, which is actually back a couple of slides. Here's our standard deviation, 0.02, and divide by square root of 17. So if we do all of that, you get 2.450 as your lower bound and 2.478 as your upper bound. So what we can say is that we are 99% confident that the mean weight of pennies minted after 1982 is somewhere between 2.45 and 2.478 grams. Okay, we can also find the sample size given a margin of error for the population mean. And that's done this way. So basically what you have to do is you have to take z alpha over 2, which is going to be a critical value, multiply by your sample standard deviation, and divide by your margin of error. And then you square that. And again, anytime you're calculating sample size, you always round up. So let's go back to the pennies. We want to know how large of a sample would be required to estimate the mean weight of a penny manufactured after 1982 within 0.005 grams with 99% confidence. And we're going to assume our sigma is 0.02. So we calculate our z. This is 99% confidence. So again, this is 0.005, which we already discussed. So that's 2.575. S is 0.02 because that was given. And your error that we're interested in or that we're okay with having is 0.005. So what we do is we take our z value, our critical value, our 2.575, we multiply by our sample standard deviation, which is 0.02, and we divide by our error, which is 0.005, and then we take that quotient and we square it, and we get 106.09. And like we already talked about, you always have to round up, so n is going to be 107. Okay, so I want to show you a little slide that kind of shows you how to put all of this stuff together. So this is very helpful. This is in your textbook, but this will kind of walk you through what exactly should you be doing when. So if you want to know what to do, basically you start with this question. It's like a nice little flow chart they have. So which parameter are we estimating? So if you're estimating a proportion, you just go to this purple box right here. Basically, provided that n times p hat times 1 minus p hat is at least 10, you construct a confidence interval, just like we already learned. If you're finding mean, which is the other thing that we do, you ask yourself whether or not sigma is known. So if it is known, then you ask yourself if it's greater than or equal to 30. If it is, then you compute your z interval, okay? And if it's not, then you ask yourself if your population is approximately normal with no outliers. So you're going to look at your box plot and your normal probability plot and evaluate. And if it's not, then you have to use some non-parametric methods, which we have not yet learned. But if it is, then you can compute your z interval. Now, if sigma is not known, then you ask yourself if n is at least 30. If it is, then you compute your t interval. Okay, so this is an approximation of z that's a little more conservative. If n is not at least 30, then you ask yourself if your population is approximately normal with no outliers. So again, you do your normal probability plot and your box plot. If it's not normal, then you can't do anything with it right now. You would have to use a non-parametric method. But if it is normal, then you go ahead and compute your t interval. So let's walk through a couple of additional questions. So first thing we want to do is go ahead and determine the critical value, z alpha over 2, that corresponds to a 96% level of confidence. So if you think about 96% level of confidence, that means your alpha is going to be 0.04, because that's 4%. If you take 0.04 and divide it by 2, you get 0.02. And then what you want to do is you want to look in the actual body of your z table, and you want to go ahead and try to find something where you have 0.02 as your actual value. And what you should find is that you find negative 2.05 is the actual value. And if you recall, when we talked about critical values, since you have this symmetric property of your normal distribution, you can ignore the fact that it's negative and just say that it's a positive 2.05 because that also corresponds with your 96% level of confidence. All right, now we want to find the t value such that the area in the right tail is 0.025 with 14 degrees of freedom. So this time you're going to go to your t table, you're going to go down until you get to 14 degrees of freedom, and then you're going to kind of scroll yourself to the right until you get to 0.025. And once you do that, you should end up with a critical value of 2.145. Okay, let's say we want to determine the point estimate of the population mean and the margin of error for a given confidence interval. So this is actually kind of backwards. Everything else we did, they gave us data and we had to find the confidence interval. This one, they give us a confidence interval and they want us to tell them what the actual mean is. So if you recall, I did mention that the mean is always going to be smack dab in the middle of your confidence interval. So if you think about the numbers 12 and 20, What you want to do is you want to find the number that's right in the middle of those. And if you think about it for a minute, you'll probably conclude that it's 16. If you'd like to actually figure it out mathematically, you would do 12 plus 20 and then divide that by 2. And you should get x bar is 16. And then your margin of error is going to be how far away your mean is from your upper bound or from your lower bound. So all you have to do is take your mean, your 16, and subtract your lower bound, which was 12, and you get your margin of error is 4. So that is choice A. All right, here's a similar one with p hat. So again, they give us a confidence interval, and then we want to find the upper and lower bounds. So what we need to do for this one is we need to find what number is in the middle. So if you want to figure out what's in the middle, again, you do 0.223 and add it to 0.285, and then divide by 2. You get 0.254. And then you want to figure out how far away is 0.254 from my lower bound or my upper bound. So you subtract, and you get 0.031. So your p hat is 0.254, and your margin of error is 0.031. Okay, a survey found 195 of 250 randomly selected internet users have high-speed internet access at home. We want to construct a 90% confidence interval for the proportion of all internet users who have high-speed internet access at home. So it's important to remember how to calculate your lower and your upper bound. So what you're going to do is you're going to take your p hat, which you have to find, and you're going to subtract your critical value multiplied by square root of p hat times 1 minus p hat over n. And then to find the upper bound, you add it this time. So if you remember the 90%, that actually goes with 1.645. So what we have is 1.645 times, and then our p hat is going to actually be 195 over 250, because those are the number of people who have high-speed internet. So if you calculate that, it's 0.78. So what I really have is something where I have 0.78 plus or minus, so that's going to give me both my lower bound and my upper bound, times 1.645, that's my critical value, multiplied by the square root of 0.78 times 0.22 over 250. So I'm going to punch that in my calculator now, see what we get. And what I end up with is 0.78 plus or minus 0.043. And if we actually do that, if we add our values and subtract them, we get 0.737, which is calculated by taking 0.78 plus and minus 0.043. And then you also add it, and you should get 0.823. So this is your 90% confidence interval for the proportion of internet users who have high-speed internet access at home. All right, now let's say you want to estimate the proportion of adults who have a fear of snakes. What sample size should be obtained if you want the estimate to be within 3 percentage points with 95% confidence if you don't use any prior estimates? So if we're not using a prior estimate, we need to use this formula here, which maximizes our value. So we have 0.25, and then we have z alpha over 2. Now, if you recall, 95% confidence goes with a critical value of 1.96. And then our E that we're willing to deal with is 3 percentage points, so that's going to be 0.03. So what we do is we take 1.96, that's our critical value, divide by that margin of error that we're okay with, which is 0.03, and then we square that value, and then we multiply by 0.25, and we should get n equals 1067.11. The 1 is repeating. Now, if you remember, anytime you're calculating sample size, you always have to round up. So that is going to round to 1068. Here, we're shown a simple random sample of size n is less than 30. From the normal probability plot and the box plot, we want to decide whether a t interval should be constructed. So if you remember kind of that flow chart that we went through, if we ended up with a sample size that was less than 30, what needed to happen is that we needed to have a normal distribution. okay, or something that was approximately normal. So if we look at our probability plot, our normal probability plot on the right-hand side, all of our red dots are within our bounds, so this looks good. And then if we look at our box plot, we don't have any asterisks, so that means we don't have any values that would be considered outliers. So this one, it would be fine to construct a t-interval. Okay, I think this is the last one. So let's say a simple random sample of size 15 is drawn from a population that's normally distributed. Sample mean is found to be 64.3, and sample standard deviation is found to be 5.6. And we want to calculate a 95% confidence interval. So if you'd like to do that, what you go ahead and do is you take your X bar, which will be 64.3, and then you have to look up your critical value. So you're looking for T alpha over 2. Now, if you recall, if we have 95%, then our alpha value is going to be 0.05. So if you divide it by 2, then you get 0.025. So what you would need to do is you'd need to look up the value on your table that goes with n minus 1, which is 14 degrees of freedom. So you go down to 14 degrees of freedom on your t-table, and you go over to where you see 0.025, and then that's going to be your critical value. You multiply that by S, which is your sample standard deviation, which in this case is 5.6, and then you divide by the square root of 15, because that's your sample size. And then for the upper bound, you do the exact same thing, except you add instead of subtract. And if you go ahead and do that, then you get 61.2 to 67.4. So that is it for this week. Please